welcome, Robert, and you need no introduction to our group. Thank you for taking the time and appreciate your commitment really to the integration of faith and science and your passion for learning and for spreading the Christian message. And so let's
Okay.
hear that small voice.
All
And
right.
we'll begin.
Well, yeah, I've told my voice is not very small,
That's
but
right.
this talk was motivated partly because of the new results coming in from the James Webb Telescope and also new
Okay.
frontiers
Yep.
in cosmological observation. So here
Okay.
we have a picture of the heavens, and down at the lower right, a picture of Elijah listening to the still small voice.
Yes.
And we are, as I said, entering, let's see if there we go, a time in the next 10 to 15 years that will introduce a wealth of cosmological information and information about astrophysics, observational information that is really unprecedented, though that word gets used too often. The thing you're seeing at the upper right is one part of the LIGO Virgo setup, which is the gravitational wave interferometer. And we have now lots of events from gravity waves, and these facilities are getting upgraded. So we're going to see a lot more information about gravitational waves in the next 10 years. There's the dark energy spectroscopy instrument, DESI, that is also beginning now and well began in 2025 to collect information about dark energy. The Euclid satellite is launched rather in 2025, and the South Pole Telescope is coming online to collect other kinds of information. There's the Nancy Grace Roman Grace Space Telescope set to go up in 2027. The Simons Cosmic Microwave Background Observatory, I think in the Atacama Desert, set to come online. The Vera Rubin Observatory is supposed to begin taking data this year. SphereX in 2025 is taking data. And then we have the James Webb Space Telescope that launched a couple of years ago. And this is a picture of what it looks like, where you've got the solar panels that collect the sun's energy, but protect the observing part, which is this honeycombed like structure here, from sun's rays so it can take data. And it was named after the NASA um, official, James Webb. I suppose I should call him an astronomer. And Northrop Grumman's the one who drew the picture here. So here are some. I thought it's always fun to start off showing pictures. I am not an observer myself, but this here shows you pictures of the kind of thing that James Webb observes, and the I think the left-hand side is the detail we get from James Webb, whereas the right came from Hubble in these bottom two pictures. The top two ones are from the top one, sorry, is also a James Webb picture. So there is an example of what previous observation was of these two spiral galaxies that are crashing into each other, um, that we can get now. And again, here, Hubble on the left, I think maybe I interchanged left and right. So Hubble was on the left and James Webb is on the right. And this is a close up of the detail you can get from James Webb. Over here, we have an example of what Hubble saw in 2016 of various galaxies where the circles are supernova that went off. And the James Webb telescope is able to resolve this in much greater detail, you can see, for example, that this part right here, can you see my cursor moving?
Yes, I can.
Yeah, is there's a lot more gas and structure around this supernova here, and likewise this one here compared to the earlier image, and so on. These are all being gravitationally lensed. It's why they're stretched out
Hmm.
relative to a very heavy source in the middle. So
Interesting.
Hmm.
uh, the James Webb Telescope sends its information to this deep space network that is stretched over three places in the world, and it sends about 28 million bytes per second. Uh, and so there's so much data coming in that you need these three stations to collect it all. And partly based
Amazing.
on the time of day, it's basically stretching over the three nighttime time zones that you can have around the world between North America, Australia, and Europe. So,
Hmm.
so the point of showing you all that is to emphasize the fact that our ideas about the universe and how we understand it are very much guided by data and more so than they ever have been
Hmm.
um, in even the last 10 years. And what they are doing is providing further information about this Big Bang model. This picture is probably now about 15 to 20 years old, that
Hmm.
discusses how we understand the universe from its earliest instance, about 13.7 billion years ago, to its rapid expansion and then slower expansion now, which is accelerating, going from the cosmic microwave background of the imprint of the last of the time when the universe became transparent to radiation. There's a dark era that James Webb is going to shed light on. And after that, the first stars light up when it becomes cool enough for stable atoms to form. That's after this stable atoms form. When it becomes
Right.
cool enough that structure can form, I should say. I got a bit
Right.
ahead of myself. And then after that, stars and galaxies form, and James Webb is going to tell us something about what's going on between this part here that we know
Hmm.
something about, and this part here that we know something about, and this part in here that we know very little about.
Hmm.
So we have this picture of the Big Bang model that goes from beginning to cosmic microwave background to an era where there are atoms, but not really very much structure. And eventually there's enough clumping that the first stars light up, and we have galaxies forming, and then we have the current picture now. But this model relies on a number of assumptions. One
Hmm.
is the cosmological principle of homogeneity and isotropy. One is general relativity. Another one is the standard model of particle physics that assumes there are six quarks, six leptons, a Higgs boson,
Hmm.
electromagnetic weak and strong interactions, that there is a distribution of dark matter, that there is dark energy or a cosmological constant. So I'm going to talk about what each of these assumptions are
Right.
because they are the ones that bear influence on how we um, reflect and understand this whole picture in theological terms. So the first is the cosmological principle, which is rooted in the Copernican principle, going all the way
Hmm.
back to Nicholas Copernicus in in the
1453, I think.
1400s.
Yeah.
Yes. And basically the simple way of saying it is that we should be wary of assuming that our own observational viewpoint is unique. Um, and of course, his idea was it looks like everything goes around the Earth, but maybe not. maybe things are going around the sun. And if you assume that our observational viewpoint is not the special one around everything which everything rotates, you get a more coherent understanding of the motions of Mercury, Mercury and Venus and Jupiter and Mars and Saturn that had rather bizarre behavior in their motions over the course of time relative to the night stars. So this principle is applied today with this observation that the universe looks the same in all directions on large enough scales. We don't, for example, see a huge amount of matter lumped in one direction relative to a big voids in another. When we look at large enough scales, it's spread out pretty evenly, kind of like a network of spider webs or filaments. So that looking the same in all directions is what we call local isotropy. So that's the cosmological version of what of geocentrism, which is what people saw in the, well, prior to 1500. And even today, it looks like everything goes around the Earth. But if we say, well, that's not really a special viewpoint, and we add the Copernican principle to it, we get this first assumption, the cosmological principle, that the universe is homogeneous and isotropic about any point. So, in other words, this assumption, the isotropy that we see combined with the Copernican idea, would say that if we go zillions of miles away from here, observers will see that their view of the universe also looks the same in all directions. We can't prove that principle. We can't prove that, but if we accept it, then we come to the conclusion that the universe has these two basic features. It's isotropic about any point. In other words, anyone anywhere will think it looks the same in all directions. And as a consequence, the universe is homogeneous, like milk. If you go to any particular, if you take a big jug of milk and go to any point in the milk, it looks the same. Or maybe I should not use milk, which is a bit too smooth, but a brick wall. A brick wall has structure, but if we look at one little part here, it looks roughly the same as the part over here, the part over here, and so on. So homogeneous means it looks the same in all places. Isotropy means it looks the same in all directions. The cosmological principle says that at any place in the universe, both of these features are true.
Mm.
So then the next thing that comes into the mix is general relativity, which is the idea that gravity, instead of being a force, is really the warping of space and time. And in other words, space and time are curved or warped like the way a heavy ball warps a rubber sheet, and that warpage is what we perceive as gravity. Now, this is a somewhat complicated mathematical theory that was presented about 100 years ago. 110 years ago, sorry, a little more than that, 110 years ago last November. And it made a retrodiction, namely that if you believe the theory was true and used it to calculate the motion of Mercury about the sun, you found that this warpage of space made its perihelion shift relative to Newton's theory by 43 seconds of arc every century. And that had been observed in the 1850s by Leverrier. And despite taking into account the effects of Jupiter and Saturn and the other planets on Mercury, there was still this excess. And Einstein's theory predicted that excess, or rather retrodicted it since we'd seen it. But it also made a prediction, namely that a light ray will be deflected by a gravitational field. In particular, it made this prediction that 4 times the mass of an object times Newton's constant divided by the speed of light, and the distance the light ray passes from the center will be the amount of deflection. And if you put in the numbers for the sun, it's about 1.75 seconds times the radius of the sun divided
Hmm.
by the distance, the closest distance of approach the light ray has. So the biggest this number can be for the sun is 1.5 seconds of arc. A second of arc is 1/3600th of a degree.
Hmm.
So this was observed by Eddington by in a clever way of looking at a pair of distant stars when the sun was blocked by the moon during an eclipse, and then comparing that angle to what you would see when the Earth was on the other side of the sun at night. And indeed, he saw about 1.75 seconds. It was actually not quite that number, but the error bars were within limits. And over the decades since, it's been refined. So we now agree with this observation, agrees with this prediction to better than 1 part in 1,000. So the point of general relativity is that gravity bends light and it slows time down. The warpage of time means that clocks tick differently way over here compared to nearby a heavy object. Time is slower near heavier things, by which I mean literally all physical processes, clocks, heartbeats, food digestion, growth of plants, everything is slower near heavier objects. We are
Hmm.
aging slower because we're on the surface of the Earth than astronauts would in a space station, or those that will be soon going around the moon. Now, the next assumption is the standard model, which I'll sketch out. And what we've discovered in the 20th century is that all matter is made of the things that I have represented on this slide. There are 6 different kinds of quarks: up, down, charm, strange, top, bottom, and 6 different kinds of things called leptons, which are electron and its neutrino partner, a muon and its neutrino partner, and a tau and its neutrino partner. The lines represent interactions of all the non-gravitational forces. So quarks feel gluons, but nothing else does except for gluons that interact with themselves. These leptons and all the quarks interact with the photon. The W and Z bosons are the forces of radioactivity, which interact with all of the leptons, all of the quarks, and the Higgs boson, which in turn interacts with everything. So it's a bit of a complicated
Okay.
diagram. The Higgs boson, which was the last particle to be discovered, is the particle that basically gives a drag to everything, all of the leptons and all of the quarks. And the stronger the coupling, the greater the drag. This drag is what we perceive as the mass of these things.
Hmm.
So here's another way of looking at it. Uh, what we know now in 2025 is that all normal matter is made of electrons, up quarks, and down quarks. I've got 3 different colors for the quarks because those represent the 3 kinds of nuclear charge these things can have. Protons and neutrons, which are what the nucleus of atoms are made of, are each made of all these things. Protons are made of 2 up quarks and 1 down. Neutrons are made of 2 downs and 1 up. And then around a nucleus, electrons orbit. When radioactive decay occurs, these electron neutrinos are emitted. And for all normal matter in everyday life, snow, human body cells, gold, lead, anything is made of combinations of this. What is puzzling is that this pattern is twice replicated exactly the same way. So the charm and the top are just like the up, except they're heavier. And the strange and the bottom are just like the down, except they're heavier. In fact, the middle group is of medium weight, and the group at the far right is of heavy weight, but not with any nice discernible pattern, except more heaviness. But they're not heavier in the same ratio. The rows are grouped by electric charge, and I've listed that here. And then we have these other particles that mediate forces. The photon mediates electromagnetic attraction or repulsion. The gluons are what stick these guys together into protons and neutrons in the nucleus. The weak bosons govern radioactive decay, and the graviton is what everything feels via mass. And then there's the Higgs that all of these things feel that gives particles their mass. So that's what we know now. And if you took the particle physics course I once taught, this is
Yeah.
what you would learn from it. So there's a lot of information in there, but I want to say this is an observational foundation of how we interpret the Big Bang.
Right.
And so you don't need to remember all those details, but I feel morally compelled to say them correctly. Uh, in the 21st century, there have been two big observational triumphs in the first quarter of this century. One in 2013 was the discovery of the Higgs, which was predicted 50 years earlier, but took 50 years to discover in particle physics experiments. The other was the detection of gravity waves. That Einstein's theory predicted gravity was like the warpage of space, and the idea was that if a mass could be shaken, then it's the warpage it caused around it would make ripples in space, analogous to the way that if you put a mass on a rubber sheet and shook the rubber sheet would vibrate. Well, space itself can vibrate. Now, these vibrations are pretty feeble, but if a pair of black holes crash together, you get enough vibration to be detectable. And that's what LIGO saw first in 2016 for the first pair of black holes crashing together that we could observe. And now there are hundreds and several hundred events of this type. So out of all this stuff comes a notion of a universe that is not just sitting still, but is actually changing with time, and it could be expanding. Well, we observe it to be expanding at present. And because of this, it could be expanding, but then later contracting. It could be expanding to a static state. It could be expanding to a state of constant speed, or it could be accelerating. Those are basically the four possibilities: decelerating, coasting to a constant, coasting to constant speed, or accelerating faster and faster. The rate of expansion is given by this parameter AH naught, which is basically the ratio of how large the universe is, given by this parameter A, the rate of change of how large it is divided by its size. And I'll show you an equation that comes from general relativity. So A dot over A is this parameter H, and it's given by its value right now, multiplied by all this stuff that depends on the size. One is a term that goes like 1 over the cube of the size, and the coefficient is the amount of dark matter plus normal matter. This part that goes like 1 over the 4th power is radiation. This part depends on whether the curvature is like a sphere or a saddle or a tabletop. And this part is the dark energy part,
Mhm.
which depends on a parameter W. So just to show you that people calculate this with an equation, if any of you have ever taken calculus, you could, from this equation, determine how the universe changes with will change with time given its initial value and given these numbers here which cosmologists measure. They measure all of these numbers in this equation. If W is -1, then you get a zero here, and that's when the dark energy is a cosmological constant.
Mm.
So this is what you get when you calculate how that size factor A, the scale factor as we call it, changes with time. So early in the universe, when A is tiny, the tinier A is, the bigger this number is, and this dominates the radiation. But as it gets bigger, this dominates, and then this dominates, and so on. So you get these three kinds of curves where if radiation were all there were, then the scale factor, the size of the universe would decrease this quickly. If there were only dark matter and normal matter, it would decay like this. If there were only dark energy, it would decay like that. So you can see that early in the universe, this is the biggest, and then matter is the next. But as the universe expands, these two cross over and then matter dominates. But as it expands further, eventually this dark energy, which is tiny to begin with, is going to win. And this seems to be the universe we live in, is a combination of the red, the blue, and the green curves put together. I've separated them so you can see the effects. And to show you that, as I said, cosmologists measure these things. This is normal matter. This is dark matter, and they are these numbers which are normalized in units of the value today are known very precisely. And there are a number of other parameters as well that I have not explained. There are lots of them, in fact. And what is quite remarkable is they are known to like tenths of a percent. And except for the rate of expansion now, which is could be a lot better, and this number is rather controversial. The dark energy is known again pretty good, and so on. There's lots of these things, and cosmologists measure them all. And that's those instruments I showed you at the beginning, including James Webb, are over the next 10 years going to sharpen these even more precisely. So, what I'd like you to get from this is 50 to 60 years ago, when we were kids, these numbers were hardly known at all. We had we knew the universe was expanding and we were developing a vague idea of how that might work. But now there is a precision science going on here. And it's going to get even more precise. This picture, maybe some of you have seen, it is a plot of the amount of power, uh, correlated power at various angles. And the angles here are very wide. So what astronomers do is they look at one place in the sky and then they look at another place far away. So since it looks like we're in a sphere, the farther away they are, the bigger the angle. And the closer 2 points are, the smaller the angle. And then we ask how much power is in the background radiation, how much correlation is there between the power at these two different points as they are far apart over on the left or close together on the right. And we get this wiggly curve that we can predict, that we measure, sorry, I should say, from observation, and that cosmological model predicts, which is the red curve. And you can see it's pretty good. between theory and experiment, with some variation way over here at big angles, and depending on the instrument observing, more variation here at tiny angles, but these other observational projects are sharpening this up. So these older ones are WMAP, and the green ones are newer ones from a project called Quad. And even this is now 15 years old. They're getting more precise. So the point of showing you this next part is to say, first of all, cosmology has gone from a rather broad science to a precision science over the last 50 years. And we have pretty good agreement between observation and theory, but there are puzzles. We don't understand the origin part very well at all. We don't know why or even if the universe is homogeneous and isotropic as much as the assumptions assume they are. We don't know how this dark energy evolves. Is it indeed constant or is it changing with time? Baryogenesis refers to the origin of normal matter, and we don't understand that. There are also puzzles in how normal matter clumps together to give hydrogen, helium, lithium, beryllium, the light elements that we see. There is a problem in the model in the prediction of lithium abundance. When we look at those neutrinos that I told you about earlier, they have very light masses. And we have constraints on that from particle physics, but we get different constraints from cosmology. And when we look at the cosmological constraints and compare them to particle physics, it looks like the sum of the masses is negative, which makes absolutely no sense. I already told you when I showed you that list of things that the Hubble constant is not well understood. In fact, there are two different collections of measurements. One gives a value of about 67. The other gives a value about 74. This is kilometers per megaparsec per second. In other words, we don't know the present rate of expansion of the universe per unit time. Observationally, we have two sets of conflicting measurements, and it was thought 20 years ago that we'll do them more precisely and get agreement. Well, in fact, what is happening is as precision is increased, they diverge. In other words, measuring it one way gives precise values that disagree by 5 standard deviations with measurements made another way that give precise values. We don't, that asymmetry in the measurement of power at different angles is still not properly understood, and we don't understand the formation of supermassive black holes. So there's a lot of puzzles, which is good news if you want a job in cosmology, because there's lots of things to do. And we don't know what dark matter is, and we don't know if there are habitable exoplanets. So I'm going to now shift. That's sort of a broad picture of the science. And if you go to the James Webb Space Telescope page, you find that this is on it. We wonder, it's our nature. How did we get here? How does the universe work? And are we alone in the universe? So these questions are not just scientific questions. They're rooted, I would contend, in theological questions. Sorry. Did I do the right thing here? Yeah, they're rooted in what I would call theological questions. And we have, I want to talk about some of these puzzles and how they are. Sorry, is there a question? I know I've said a lot.
Yep. No, I think we're fine.
Okay. They're rooted in I want to talk a little bit more about these scientific puzzles before getting to the theology. So let me just give you a flavor of what they are. So I told you about this assumption of isotropy, that the universe looks the same in every direction. Well, it mostly does, but the data from the Planck satellite show that there is a bias in the northern hemisphere relative to the southern hemisphere that is statistically significant. In other words, the average temperature of the background radiation is a little bit different in the northern hemisphere relative to the southern one. And you might say, well, is that buried in the errors? Well, these observations are showing, well, no, it isn't. It's like if you compare it to the Earth, it would be as though the temperature at the North Pole were a little bit warmer than the South Pole. And on Earth, well, I mean, that actually is a little bit true. And we can understand that because Antarctica has land and the North Pole is on water. But in the universe, it's not supposed to be true. It would mean there's a bit of a bias. Now, we're going to look at that more carefully over the next 10 years. Maybe it'll go away, but at the moment, it's there. I mentioned this lithium abundance problem. Um, Lithium is the third lightest element, and our model of the Big Bang and how nuclei form is very well explained, except the prediction of the amount of observable lithium in empty space is smaller, or rather, the prediction is larger by a factor of 3 to 4 than what we actually see. And we don't know why. And I mentioned this funny thing about the masses of the neutrinos. Um, the sum of the total of neutrino masses determine the expansion of the universe, and it's imprinted on the cosmic microwave background. But this sum of masses is below the minimum that particle physics experiments say has to be present. So that those are specifics of those early universe puzzles. And because I work on black holes, I think I'll mention supermassive black holes because the James Webb Telescope has told us something about this. So here's a sort of schematic picture of how a black hole would warp space around it and distorting galaxies that are well behind it, but the light from them skirts the black hole and so stretches them out and distorts them and so on. So the James Webb Telescope has found black holes that existed 570 million years after the Big Bang. There's the picture from the Webb Telescope over here, and here's the spectrum they get that where this peak shows you the a massive amount of radiation that is near the black hole collected due to its super heavy nature. And what we find is that this very heavy black hole exists very early in the universe, um, much earlier than we can understand black holes to form based on known mechanisms. In other words, we have known mechanisms for how black holes should form, but it takes time for those mechanisms to work and make very heavy black holes. And it looks like it should take over 1 billion years, yet the James Webb Telescope found one that is super heavy that's taken only 500 million years. We don't know why. So, furthermore, what Webb has shown is there are more galaxies in the universe than we expected. They're brighter than we expected, and they all seem to have very heavy black holes at their cores. So, as I said a moment ago, these black holes are too big to have started from one as heavy of a star and grown. So, maybe they formed initially with 150 times to be as 150 times heavier in the sun. But if so, we don't know how it happened. There needs to be some other formation mechanism of these things. Now, this is a scientific problem. Uh, as opposed to a theological one. But I think the implication for theology, or for those that are believers, is when you hear scientific reports about how we understand X, Y, and Z, you should always take it with a grain of salt because sometimes things are not as understood. And then finally, there are exoplanets. Here's one, GJ 486b, that we're finding. We've got like thousands of exoplanets now, 3,500, I think, or something at last count. These are planets that are orbiting stars that are not the sun. And we have yet to find one that can support life. It's been thought that maybe they do. Here's WASP, a picture, a schematic diagram, an artist's concept of K12-18b, as it's called. There's another one, WASP 96b, a gas giant with water vapor. There's another one, TRAPPIST 1b, which is the first planet where we've seen heat emitted. It's not that the other ones don't, it's just that the heat is hard to see. WASP 39b is another gas giant with sulfur and carbon. We can observe photochemistry on other planet. Actually, it was 3,500, 5,800, I'm sorry. And 976 planetary systems with more than one planet have been observed. And there's a lot of other candidates that are awaiting confirmation, but so far, no life. So again, let me get to this James Webb Space Telescope where we have these theological questions. And if you looked at the reading I suggested for Polkinghorne that Ted Davis commented on, it looks like we live in a universe of rational, transparent beauty. And so I want to turn from cosmic theory and observation to cosmic theology. And this diagram to me has suggested basically three basic features that I call injection, which is a short way of asking how did all of this get here and why, direction, which refers to the development of the universe, how it works, and selection. Are we the only sentient life in the universe? So, what this picture suggests or indicates from what we've learned is that there are special initial conditions that seem to be necessary to give rise to the universe that we actually observe. Furthermore, to get the development we see, there need to be particular laws of physics instead of any old laws of physics. And furthermore, there seem to be special structures of nature that have emerged that give rise to particular features we see. In other words, there are some structures we do observe and see, and others that we do not. So our universe does not appear to be typical. And there's a huge amount that could be said about this. I'm only going to comment on three of these things. One is typicality. What do we make of the particular features of our universe? Reductionism. Is it fair to say that the whole is the sum of the parts? That any given structure we see it can simply be understood by looking at its atomistic features? And furthermore, plurality. What is our significance in this vast universe? So let's go back to Copernicus. Be wary of assuming uniqueness based on your own observational viewpoint. I mentioned this notion of homogeneity and isotropy. And I've said that isotropy, maybe it's not as isotropic as we thought it was. But this principle applied in broad terms would lead people to perhaps think that our universe must be typical. Typical. That, in other words, it would look like any old universe. But is it? Will random initial conditions generate our universe? And we now know enough about cosmology that the answer seems to be no. And so, as a consequence, should the results of cosmology or science in general be interpreted in terms of typicality? In other words, do we have to require our observations to fit this Copernican assumption of typicality or not? Uh, we can ask questions. Is typicality falsifiable? Or conversely, is particularity or atypicality testable? Um, it's been said by some people that when Copernicus came up with the idea of heliocentricity, this was a demotion of humanity. We were no longer at the center of the universe. We were simply a planet orbiting a star. And furthermore, all the observations of exoplanets say even our solar system isn't typical. There are lots of these things. But Dennis Danielson has pointed out that, in fact, geocentrism was actually uh, or the removal of geocentrism could be regarded as a promotion of humanity because the idea was humanity was one step away from hell, which was at the core. And by breaking out of that assumption, we could see that in fact we were not so depraved, but in fact we were promoted in a certain sense. So I think we need to be wary of secular interpretations of how scientific findings changed our assumptions. So one could ask if human significance can be given a scientific basis or not. And we can ask whether or not human significance, if such a thing is the case, can be understood in a universe that is apparently indifferent. So I think this is where this vast cosmological structure, some of which was commented on in the article by Ted Davis, leads us to theologically. What is the relationship between what we might consider human significance in some sense be to a scientific description? Oops, sorry. Oh, yeah, no, this is fine. So, related to those injection direction selection questions I asked, will random conditions generate our universe? To what extent do particular structures like black holes depend on the particular laws of nature? And getting to the selection part, we certainly know that life exists in the universe. Is it rare or is it common? And is it a matter of being fine tuned? Is life a matter of survival of the fine tuned? And the problem we're faced with is that we have many possible universes that could have existed and many possible outcomes of the structures that could exist in them, like stars, planets, and life. But we see out of all the possible things that could have happened, one of them that occurred. And I think we have to take this seriously. We're not seeing all possible structures emerge. We're seeing a very small subset emerge. Is this suggestive of a selector? Is this some kind of thumbprint of a creator? An indirect suggestion of that. And that, I think, is the theological question that emerges. I think it's part of the still small voice. Let me go to the second one, which is reductionism. So here are the pictures of the four forces of nature: electricity, radioactivity, the nuclear force, and gravity. And as I said earlier, there was this triumph of the standard model in the 21st century that the last pieces were put into place in terms of the discovery of the Higgs boson and particle physics and of gravity waves in terms of general relativity and gravity. So we now have a working description of all known forces and particles in nature. It's like we filled in the particle physics version of chemistry's periodic table that was filled in between the 19th and 20th centuries. So this is a big triumph. We now have all known structures reduced to quarks, leptons, and the forces between them. And yet, not quite, because cosmologically, we see there is something called dark energy, which is causing the expansion of the universe to accelerate, and dark matter, which seems to be clumping galaxies together. And we certainly have solid cosmological evidence of these things, but we don't know how they fit into this picture we've developed in particle physics. And we keep searching for something that goes beyond this standard model description, but we have yet to find it, and we don't know what it is. There are hundreds of possible proposals that have been presented, but none of them have agreed with observation. Particle physics observation keeps confirming this standard quark-lepton forces picture. So that's the conundrum we're in right now with reductionism. So one can ask the kind of questions that people like Robin Collins have asked. Is our cosmos somehow optimized in some way? Are there limits to a reductionistic description of nature? To the extent that reductionism works, are we closing the last gap for God? Or is, in fact, this reductionism pointing to deeper intelligibility of a subtle creator? And if you read the Davis article, he and Polkinghorne, and me too, would opt for this latter version. So I think we have this theological question of how we move beyond reductionistic intelligibility to God, the mind of the universe, but also to God as a God of love, which is what Christian faith would assert. So those are some of the theological questions that I think emerge from reductionism. And let me talk about plurality, which is really motivated by all the astronomical observations of exoplanets. We found that planets are common. There's 3,000 plus, 5,000 plus extrasolar planets confirmed. I should update this slide. But none are Earth-like so far. Some come close. Now, this is because, in part, there's an observational bias. It's easier to see Jupiter and Saturn type planets than it is Earth-like ones. But nevertheless, we can ask, are we the only inhabitants of our own galaxy? Is life rare or common? And more specifically, is sentient life rare or common? We don't know yet. But again, extraterrestrial life raises the science religion questions. Does it mean if we find it, oh, life is blind and pointless, it emerges in other places, God didn't do anything special here, or not? Or can we understand this as the creator's activity? I think we need more theological work on this. There is some. Another theological question, which I ask whenever I have astronomers talk about exoplanets, they always say, we want to find life. And I say, why do we care? And the answer they give me is puzzlement. They say, well, good question. I don't know. I mean, scientifically, why should we care at all? It doesn't matter one way or the other. But I think we care because we have this theological urge inside us to know if we are alone, both in terms of whether there's a God and in terms of whether there are others. If we find extraterrestrial life, we will need to rethink the concept of the Imago Dei, that emerges from Genesis. And we have a sociological question that if we do find them and if we could interact with them, how do we treat the alien? So far on Earth, that has not always gone well, but maybe we can learn from past experience here. So I'm going to close up now. Listening to a still small voice involves distinguishing signal from noise, and a theologian named David Palin said there are four basic attributes for God that can guide our discussion. One is that God is ultimate, as expressed in Revelation. Another is that God is holy, Isaiah 6, verse 3. Another is that God is a God of love, God is personal. And finally, God is agential, not disinterested or decoupled from the universe. And these four basic attributes of God within the Christian faith merge together to contend that the vast creation, this vast universe we see, is subordinate to the Creator. It is not decoupled from the Creator. It's not part of the Creator. It's subordinate to the Creator. What science does is, in observation and experiment, construct contrivances to filter out a signal from the noise to make sense of all of this. What faith does is listen to these results and to our urging to try and discern what is the call of God as we reflect on these observations and their meaning. So I think we're in a state of tension here. On the one hand, we have the stake of rationality from Proverbs. The wise store up knowledge, but the mouth of a fool invites ruin. But we have the urging of Job. I know that my Redeemer liveth. Despite all the suffering and pain of the world, the noise of the world, we really believe there is a theological signal pulling us toward it. And I think we live in Christian faith in this tension. So, what are the lessons here? I'm almost done. This is my last slide. We strive as individuals to be perfect, even as our Heavenly Father is perfect. We strive to yearn to hear this still small voice of God. We acknowledge our own fallibility, that all have sinned and fallen short of the glory of God, but we thrive in community. Let us consider how we spur one another toward love and good deeds, not giving up meeting together as some are in the habit of doing, but encouraging one another. The scientific endeavor works because scientists work in community. They acknowledge that they make errors, but they strive for knowledge. I think as Christians, we thrive when we are in a faith community that encourages us and corrects us, to remind us of our fallibility, yet to strive to recognize that we are made in the image of God. And finally, I think we listen for the subtle and the small in nature and in our journey of faith through it. A great and powerful wind tore the mountains apart and shattered the rocks before the Lord, but the Lord wasn't in the wind. After the wind, there was an earthquake, but the Lord wasn't in the earthquake. After the earthquake came a fire, but the Lord was not in the fire. And after the fire came a gentle whisper. When Elijah heard it, he pulled his cloak over his face and went out and stood at the mountain of the cave. Thanks for listening.
Thank you, Robert.
Thank you.